Hi everyone, welcome to your next series of lectures in intermediate physics. We'll be talking about Chapter 30, which is sources of the magnetic field. So if you remember in the last chapter, we were talking about the force felt by a current in an external magnetic field. And here the word external is kind of a key word. We were talking about the force felt by a current or the force felt by a moving charged particle. In this chapter, we're going to be talking about what causes magnetic fields, and it turns out currents cause magnetic fields. So not only can a current feel a force from an external field, that is a field it's not creating, but it also creates its own field. So those words are important to pay attention to as we move along. So for an outline, your chapter actually starts out right away with the Biot-Savart law, but my notes start out with some more experimental results and then eventually get to the Biot-Savart law. I talk about Ampere's law in my notes before you're going to get to Ampere's law in your chapter, and we talk about Gauss's law on magnetism and also magnetism in matter in this chapter. So to start with an experimental result, you'll remember from the last set of lectures that Hans Christian Ørsted, you don't need to remember his name, noticed that compasses are deflected near a current carrying wire. And you can actually measure how much they're deflected and come up with a strength of a magnetic field from that. So the strength of the magnetic field that you come up with happens to be mu0 divided by 2 pi times your current I divided by R. So R is your radial distance away from this wire. So R is in any direction your radial distance away. It is not a radius, but a radial distance. Slight difference there. Okay, so that's our magnitude of our magnetic field. What about our direction? So our direction is shown with these blue arrows in this image, and we can get the direction from one version of our right-hand rule. So right here, you'll see we've got a right hand with the thumb sticking in the direction of positive current flow. If our right-hand thumb is sticking in that direction, our right-hand fingers will curl around that wire in the direction of our magnetic field lines. So our magnetic field lines here are curling in that direction. It would make sense to talk about this using the symmetry of cylindrical coordinates and to say that maybe the direction is in the phi hat direction if we're using cylindrical coordinates. Right? So we've got a magnitude, we've got a direction from the right-hand rule. There's one thing I've introduced in this equation. It's this mu0 or mu0. That happens to be the permeability of free space. So the permeability of free space is what we use when we're talking about our magnetic fields, as opposed to the permeativity of free space, the epsilon naught, that we were using with our electric field. So permeability as opposed to permittivity. All right, so mu0 has a value, it's just a constant. It is 4 times pi times 10 to the minus 7. And our units are in Tesla, meters over amps. So using that set of that constant with that set of units would give us our magnetic field in Tesla, as long as we have our radial distance in meters and our current in amps. Okay, so now that we have that information, we can combine that information with something from our previous chapter, and we can look at the force between two parallel wires. This is an interesting problem. It has an application in what's called a current balance that we'll talk about in a couple pages here. So if we picture that this wire, number 2, has a current that we'll call I2, we can stick our right-hand thumb in the direction of current and notice that our fingers would curl around in this direction, so that we have a magnetic field that's being created by current number 2. We'll call it B2. So we just found out that B2 should have a magnitude of mu naught divided by 2 pi times current number 2. And we want to look at it at the location of wire number 1. So we want to look at it at this distance A. Right? So that would be B2 evaluated at that location of wire number 1. Okay, so from the last chapter, we know that if wire number 1 has a current I1, and it's sitting in this external field we'll call B2, it's going to feel a force. So we'll call it the force on wire number 1. And that force is going to be on the current in wire number 1 and along whatever length of wire number 1 sits in this magnetic field. And we're going to cross that with the strength of B2. Now we know that a cross product is just going to take these magnitudes and then the sine of the angle between them. Well, because these are parallel wires and because this parallel wire is going to cause a magnetic field that's at a perpendicular direction, this sine just becomes 1, right? It's sine of 90 degrees. This is a right angle right here. So our force on wire number 1 is just the current in wire number 1, the length of wire number 1 that's sitting in the magnetic field, field number 2. If we plug in the numbers that we have for all this, we have some constants up front. Don't like when that happens. We have some constants up front that are mu 0 and 2 pi. We have our current in number 1, our current in number 2, our distance between the two wires, and this length of number 1, which they've actually just labeled L. And it turns out we could do the same sort of exercise for the force in wire number 2, and we would get the same magnitude. So you can go through this exercise that you get the same magnitude, but actually in opposite directions. So if I picture my magnetic field lines are going to loop around like this, I'll draw it. Actually, your book has them drawn in green, so I'll draw it in green. So current number 1, when we reach the location of wire number 2, that magnetic field is actually going to be going in this direction. So that's the magnetic field caused by wire number 1. And we can figure out that the force that wire number 2 is going to feel because of this magnetic field from wire number 1 is going to be an equal magnitude. But if we use our right-hand rule, it's going to be in the opposite direction. So this is our force. I can't write a small 2. Our force on wire number 2 is in the opposite direction. So one of the results we're going to see from this parallel wire is that if our currents are in the same direction, we are going to see a force that's attractive. And if instead our currents are in opposite directions, our force is going to be repulsive. So we're going to see our wires repel. And a lot of times, because we're talking about force and we've got currents and lengths, a lot of times we can talk about, instead of just force, force per unit length, so how many newtons per meter. And if I do that for this problem over here on the right-hand side, you're going to have mu 0 over 2 pi, I1, I2, and this distance between them. So in our example, we didn't use a D, we used an A for our distance between them. Yes. So the form of this equation actually looks a little bit like our electric field, right, or our electric force, but it's just a little bit different, right? So this would be the force on either wire because of the other wire. And again, if our current's in the same direction, it's attractive. And if our current's in the opposite direction, we're going to have a repulsive thing, right? So one of the applications I said was something called a current balance. So there's an apparatus that you run current in two wires in opposite directions, so it's repulsive. And so you can kind of levitate one wire above another. And if you're levitating that wire, you're balancing gravitational force with this repulsive force from the magnetic fields. And again, you talk about your force per unit length of the wire. So you're gonna run current through these wires in opposite directions to balance out, and you've got these wires separated by a certain distance. So if you run what you think is 1 amp in each of your wires, and if you try to separate those wires by 1 meter, then your force per unit length should be 2 times 10 to the minus 7 newtons per meter. So that actually, you have a working definition of what a newton is and what a meter, and that actually helps you define what an amp is in terms of this force equation and in terms of force and distance that you have measured by other means, so by other standards. And then of course your Coulomb is 1 ampere times a second, right? We could define our Coulomb in that way. And that's an operational definition that you can actually measure in terms of standard newtons and standard meters. All right, this is a good place to pause for now. We'll start with Ampere's law on the next recording.